Let's talk about population ecology. Ecology is the study of interactions between organisms and their environment. This includes both abiotic and biotic factors. Biotic factors are living components or once living, like plants or animals. Abiotic factors include non-living components like temperature, soil pH, light, and water. Population is any group of individuals of the same species living in the same place at the same time. A community is two or more populations. Is this a community or a population? A fallen tree holds a thriving community of organisms because there are many populations living there. Factors that affect populations. Geographical range is where the animal has been seen, usually on a map. This can change over time due to biotic and abiotic factors. For example, the northern leopard frog has been seen in the northern United States, mostly on the eastern and central areas of the country. Habitat is the area where the population lives, where environmental conditions are best suited for survival. For example, the northern leopard frogs generally live in ponds, marshes, and slow-moving streams with abundant aquatic vegetation. Niche is the role of the species in the community. An organism can have more than one role. For example, your niche at school is student, your role at work is employee, your role at home is child. This includes all biotic and abiotic factors a species needs to survive. Looking at these examples of the birds, they all have different niches. The flamingos feed by straining mud through their bills. The dabbling ducks feed on plants. The avocets feed on insects. Oyster catchers pry open shells, and plovers hunt for small insects. They're not in direct competition with each other because they all have separate niches. So populations can coexist only if each group occupies a different niche. Technologies to track animals can include binoculars, computer to record the data, capture, tag, and recapture, like the case of the migration of the monarch butterfly that they tracked in 2001. Population size, or organisms of the same type in the same place at the same time. For example, there are 2,500 students at Center High during the 2020-2021 school year. This can be determined by exact count or estimation. Population density describes the number of organisms in a defined area. For example, number of penguins per kilometer squared. It's found by density, calculated by dividing the total number n by the amount of area, A, or volume occupied by the population. So dP equals the number divided by the area, or it could be dP over the number divided by volume. What we do need to remember that area, if you're given two numbers, you're going to multiply them together, the length times the width. And if it's the volume, you multiply length times width times height to find the volume. Let's try a couple questions. There are 80,000 snow geese in a 50-hectare area in 1995. Start by writing the formula. Fill the numbers in. We have the number, we have the area, and then divide to get 1,600 geese per hectare. If 200 lemmings are living in a 25-hectare area of tundra, what is the population density of this area? We take our number, divide it by the area, and we find that there are 8 lemmings per hectare. Let's do one more. Calculate the population density of shrews per meter squared if an average of 7.8 shrews are found in an area of 14 meters by 20 meters. Again, start with the formula. Put in the numbers you know. There's 7.8 shrews in an area of 14 by 20. Let's start by multiplying the 14 by 20 and then divide 7.8 divided by 280 to get 0.03 shrews per meter squared. Population growth rate and patterns. The growth rate tells us whether or not a population density increased or decreased. And the growth rate is the change in population size over the change in time. When we're figuring these out, we start with the most recent data first. This tells us whether the number is increasing or decreasing. In 1993, the mouse population on a farm was 50 mice per acre. After 3 years, various control measures had been in place, and the population dropped to 10 mice per acre. Calculate the rate of density change. So start by writing the formula. We start with the most recent number first, so now it's 10 minus the original number of 50 over a time of 3 years. 10 minus 50 is negative 40 divided by 3. And so the answer is negative 13.3 mice per acre per year. Let's try another one. When arriving at their cabin, the Deos discovered 10,000 cockroaches roaming through their 1,000 meter squared cabin. After 1 week, the exterminators were able to control the situation and reduce the cockroach population to 10 per 1,000 meters squared. Calculate the rate of density change. So start with the formula. Fill in what we know. Now the number is 10. It started out at 10,000 over time of 1 week. So the answer is negative 9,990 cockroaches per week. Because the number went down, it is negative. Population growth is determined by 4 factors: natality or birth, mortality or death, immigration, which means individuals coming in, and emigration, individuals leaving. The per capita growth rate is the change in number over the initial number. Now, if you're given all 4 factors, then it can look like this. We add the births and immigration and subtract deaths and emigration, the factors that decrease the population, and divide it by the initial number of organisms. Or we can write it with variables. CGR can be written as a percentage. Okay, let's try this question. We have births plus immigration minus deaths plus emigration divided by the initial number. We are given the births and the deaths and the initial number. So we're going to subtract 55 from 40 to get negative 15 divided by 200. And so our CGR is negative 0.075 or negative 7.5%. Puffins are small marine birds found off the coast of Atlantic Canada. Calculate the per capita growth rate of a puffin colony based on the following population in 1999. Okay, so we have the original population and then we have all 4 factors. So let's put that into our formula for CGR. Add them separate, so 15,000 plus 175,000, subtract 10,000 plus 160,000, and then divide it by 200,000. So it's 20,000 divided by 200,000, which is 0.1. So it is increasing, it's positive. You can also say that it's increasing by 10%. Third CGR example, calculate the per capita growth rate for a population of penguins that started out with 200 and end up with 218 over a period of 3 years. So this time we're given the initial number and the number at the end. So we're going to use that for our change in number. 218 minus 200 divided by that initial number of 200, and we get 0.09 or 9%. One more CGR example. If a population of jellyfish off the coast of the Philippines increased by 9.8% each year from 2011 till 2014, calculate the number of jellyfish at the end of 2014 if their initial number was 2,500. So this time we will start with the formula, but we need to rearrange it because we were given CGR and the initial number. This time we're looking for the change in number. So the change in number is CGR times the initial number. And so we'll start out in the first year with our CGR converted to a decimal, 0.098, times it by the initial number to find out by how much it increased in that first year. Now we need to add the 2,500 plus 245 to find the number at the end of the first year, 2,745. We're going to use that number as our starting for the second year. So year 2, we need to do the same equation, same CGR, but we start with our new number that was at the end of year 1. So we find out the number that it has increased by in the second year, add that to the number we started with in the second year to find the number at the end of the second year. And then we'll do that once more because we need to calculate it for 3 years. So third year, change in number, start with the number at the end of year 2, find the number it has increased by, and add that to the number we started with for a total of 3,309 jellyfish at the end of 3 years. Now, there is a shortcut to this. You can use a formula that is similar to compound interest formula. So we start with the number and times it by itself plus the rate of increase to the total number of times we need to do it. So that would be the time is 3 years.